In the spring of 1944, Japanese fighter pilots stationed on the home islands received intelligence briefings that included a diagram. The diagram showed the Boeing B-29 Superfortress, the enormous new American bomber that was about to begin operations against Japan, viewed from above. Marked on the diagram, in precise detail, were the firing arcs of every gun turret on the aircraft. And marked just as precisely were the gaps, the angles from which a fighter could approach the B-29 without being hit. The most promising gap was directly ahead and slightly above. The forward upper turret, with its two 50-caliber machine guns, could traverse forward, but its ballistic arc was limited by the fuselage and the wing. From a narrow cone of approach, head-on and slightly elevated, a fighter could dive through the B-29's forward defense zone faster than the turret could track, fire a burst into the cockpit, and pull away before the other turrets could swing around to engage. Japanese pilots called this the head-on attack, and they practiced it relentlessly. It required extraordinary courage. A head-on closing speed between a B-29 at 250 miles per hour and a fighter at 350 miles per hour was 600 miles per hour, 1,000 feet per second. The pilot had less than 3 seconds of firing time. If he misjudged his angle by 2 degrees, he would fly into the bomber instead of past it. Many did, some intentionally. But the Japanese had identified a real vulnerability. The B-29 was the most expensive weapon system of the entire Second World War, $3 billion, $1 billion more than the Manhattan Project. And it had a blind spot. It had several, in fact. And the system that was supposed to eliminate those blind spots, the revolutionary computerized central fire control system that made the B-29 the most heavily defended bomber ever built, was, in the first months of combat, plagued with problems so severe that the commanding general of the entire B-29 force considered the gun system a liability rather than an asset. This is the story of that system, how it was conceived, how it was built, how it failed, and how it was eventually fixed. It is the story of 5 analog computers, 5 remote-controlled turrets, 5 sighting stations, and 1 sewing machine company that manufactured the mechanical brain that tied them all together. It is the story of General Electric's Model 2CFR55B1 centralized fire control system, the device that transformed bomber defense from a collection of men with guns into an integrated weapons network, and that did so using technology so advanced that it would not be surpassed until the jet age made it obsolete. To understand why the B-29 needed a revolutionary gun system, you need to understand what happened to bombers without one. The Boeing B-17 Flying Fortress carried 13 50-caliber machine guns operated by individual gunners. Each gunner was responsible for his own sector. The ball turret gunner curled into a fetal position inside a plexiglass sphere hanging beneath the fuselage, his knees against his chest, the ground visible between his feet, watched below. The top turret gunner stood in a powered turret behind the cockpit, rotating 360 degrees. The waist gunners stood at open windows on each side of the fuselage, blasted by wind and cold. The tail gunner crouched in the narrow tail cone, looking backward through a tiny window, alone. Each man aimed his own guns, estimated his own range, calculated his own lead, and fired independently of every other gunner on the aircraft. There was no coordination, there was no computer, there was no system. There were 10 men with guns, each fighting his own private war against fighters that appeared and disappeared in seconds, shouting over the intercom, ejecting spent casings, clearing jams with frozen fingers, trying to distinguish a Messerschmitt from a Focke-Wulf at a distance of half a mile while the aircraft shuddered from flak and the oxygen mask froze to their face. The system had 2 fatal flaws. First, each gunner was essentially alone. He estimated the range to the target by eye, guessing how far away the fighter was based on its apparent size. He estimated the lead, how far ahead of the fighter to aim, by instinct, training, and adrenaline. The calculations required, accounting for the bomber's airspeed, the fighter's speed and angle of approach, the ballistic drop of the 50 caliber round, the wind, the altitude, the temperature, were impossible for a human brain to perform in the 2 or 3 seconds available before the fighter was passed. The gunners sprayed. Most of them missed. Second, the gunners were exposed. The waist gunners on early B-17s stood at open windows. The temperature at 25,000 feet was minus 40 degrees. Frostbite was routine. Men lost fingers, toes, and patches of facial skin. Even in enclosed turrets, the cold was savage. Gunners wore heavy gloves that reduced dexterity, multiple layers of clothing that restricted movement, and oxygen masks that fogged their goggles. They fought in conditions that degraded every human capability that accurate shooting required. The results were predictable. Studies conducted during the war showed that bomber gunners hit their targets at rates that would have been considered unacceptable on a peacetime firing range. The vast majority of rounds fired from B-17 and B-24 gunners missed entirely. The fighters that were hit were usually brought down at ranges of 200 to 400 yards, point blank in aerial combat terms, where the accumulated errors of bad range estimation and lead calculation were partially offset by the sheer volume of fire. The B-29 was designed to do better. It was designed to do something that no bomber had ever done: make the computer do the math. In January 1940, the Army Air Corps issued a specification for a very long-range superbomber. The specification called for an aircraft capable of carrying 20,000 pounds of bombs over a range of 5,000 miles at altitudes above 30,000 feet. 4 companies submitted designs. Lockheed and Douglas dropped out. Boeing and Consolidated continued. Boeing's design, the Model 345, which would become the B-29, was selected as the primary aircraft. Consolidated's design, which became the B-32 Dominator, was kept as a backup. The specifications for the B-29 included a requirement that would have been considered science fiction on any previous aircraft: a pressurized fuselage with remotely controlled gun turrets operated from inside the pressurized cabin. The logic was straightforward. The B-29 was designed to operate at altitudes above 30,000 feet, higher than any previous bomber, and high enough that the crew would require pressurization to survive. You could not pressurize a revolving turret with a gunner inside it. The engineering of the seals and the structural demands of a pressurized rotating compartment were beyond the technology of the era. Therefore, the turrets had to be unmanned. The guns would be outside the pressurized hull, exposed to the cold and the wind. The gunners would be inside, warm, comfortable, wearing light clothing that did not restrict their movement, breathing normally, with their goggles clear and their fingers nimble. But unmanned turrets required a control system. The gunner could not physically grip the gun handles and swing the turret by muscle power as he did in a B-17 ball turret. Instead, electrical signals from the gunner's sighting station would drive motors in the turret, turning the guns to match the direction the gunner was looking. And those electrical signals would pass through a computer, an analog mechanical electrical device that would calculate the corrections that no human gunner could perform in real time. The contract for the fire control system went to General Electric. The General Electric Model 2CFR-55B1 centralized fire control system was, for its era, one of the most sophisticated weapons systems ever installed in an aircraft. The system consisted of 5 major components: 5 sighting stations, 5 remotely controlled turrets, 5 analog computers, an electrical switching system, and the Amplidyne generator motors that powered the turret drives. The 5 sighting stations were distributed across the aircraft. The nose station was operated by the bombardier, who doubled as the front gunner when not on a bombing run. The upper station, the barber chair, was a raised position just behind the cockpit, where the central fire control gunner sat in an elevated seat with a plexiglass dome above his head, giving him a 360-degree view of the upper hemisphere. The left and right blister stations were located on each side of the rear pressurized compartment behind the wings, each with a bulging plexiglass blister that provided a wide field of view. The tail station was at the extreme rear of the aircraft, where the tail gunner operated independently. The 5 turrets were mounted externally: upper forward, upper rear, lower rear, and tail. Each turret contained 2 50-caliber Browning M2 machine guns. The tail turret originally also carried a 20mm cannon, though this was frequently removed due to reliability problems and trajectory mismatch with the 50-caliber rounds. The upper forward turret was sometimes upgraded to 4 50-caliber guns to provide additional forward firepower against head-on attacks. The genius of the system was the switching capability. Any sighting station could be assigned control of any turret within its field of fire. The central fire control gunner, the man in the barber chair, coordinated the assignments. If a fighter approached from the left blister gunner would take primary control of the lower rear turret, while the upper gunner directed the upper rear turret onto the same target. If the fighter circled to the tail gunner took over. If the fighter broke off and a new one appeared from the right, control shifted in seconds. A single gunner could control multiple turrets simultaneously, concentrating the fire of 4, 6, or even 8 50-caliber machine guns onto a single target. This was unprecedented. On a B-17, each gunner fired his own guns, period. If a fighter approached from an angle covered by only one gunner, only that gunner's guns could engage. On the B-29, the fire of the entire aircraft could be concentrated on any single threat from any direction in seconds. Each sighting station had a dedicated General Electric analog computer. The computer was a mechanical electrical device, not a digital computer in the modern sense, but a collection of gears, cams, resistors, cell-sins, and differential mechanisms that performed mathematical calculations continuously and in real time. The gunner's task was deceptively simple. He looked through a reflector sight that displayed a reticle, a central dot surrounded by an adjustable circle of smaller dots. He placed the central dot on the center of the approaching fighter and tracked it smoothly. Simultaneously, he adjusted a range wheel that expanded or contracted the circle of dots to match the wingspan of the target. Before combat, he had set the target's wingspan on a dial. As long as the circle matched the apparent wingspan, the computer knew the range. From these inputs, the direction the sight was pointing, the angular rate at which it was moving, and the range to the target, the computer calculated everything else. It calculated lead, how far ahead of the fighter the guns needed to aim so that the bullets and the fighter arrived at the same point in space at the same time. Lead depended on the range, the angular velocity of the target, and the time of flight of the bullet to the target. It calculated ballistic drop, how much the bullet would fall due to gravity during its flight time. This depended on range, altitude, and the ballistic characteristics of the 50-caliber round. It calculated windage, how much the bomber's own airspeed and the wind would deflect the bullet's trajectory. The navigator input current airspeed, altitude, and outside air temperature into a panel that fed the density altitude data to all 5 computers. It calculated parallax, the correction required because the sighting station and the turret it controlled were in different physical locations on the aircraft. A gunner in the left blister, sighting on a fighter at 2 o'clock, might be controlling the upper rear turret that was 20 feet away. The sight and the turret were looking at the same target from different positions, and the angular difference had to be computed in real time as the target moved. All of these calculations, lead, drop, windage, parallax, were performed simultaneously, continuously, and automatically. The computer's outputs were shaft rotations that drove cell-sin transmitters, sending corrected aiming commands to the turret drive motors. Amplidyne generators, a type of high-gain motor generator developed by GE, amplified the computer's low-power output signals to the levels needed to physically drive the turret motors with speed and precision. The result was that the guns pointed not where the gunner was looking, but where the bullets needed to go in order to hit where the gunner was looking. The difference, the angular offset between the sight line and the gun line, was the accumulated correction of all the factors that a human gunner could never calculate in real time. The effective range of the system was 900 yards, 50% farther than manually sighted guns, and more than twice the effective range of most Japanese fighters' weapons. The computers were not built by General Electric, they were built by the Singer Manufacturing Company, the sewing machine company. This was less incongruous than it sounds. Singer had been manufacturing precision mechanical devices, sewing machines, for nearly a century. Sewing machines require tight tolerances, intricate gear trains, cam-driven mechanisms, and high-quality machining. The skills and equipment needed to manufacture a fire control computer were, in many respects, similar to those needed to manufacture a high-end sewing machine. The differential gearing, the cam followers, the precision resistors, the miniature motors, all of these had analogs in Singer's existing manufacturing capability. Singer produced the M5 Director, the fire control computer, at its Elizabethport Works in New Jersey. Production began in September 1943. The initial rate was slow. The device was complex, weighing approximately 200 pounds, containing hundreds of precision-machined components and requiring careful calibration after assembly. By the end of 1944, Singer was producing approximately 250 complete computers per week. By July 1945, the rate had reached over 500 per week. Total production, 20,794 complete computers shipped from the Elizabethport Works by the end of the war. Each B-29 required 5. The mathematics of production, 5 computers per aircraft, nearly 4,000 B-29's built, meant that Singer was manufacturing fire control computers at a pace that strained even their considerable production capacity. The computers were shipped from New Jersey to Boeing's assembly plants and to Bell Aircraft's modification center in Marietta, Georgia, where completed B-29's were lined up for final alignment of their gun turrets and central computers. The alignment process was time-consuming and exacting. Each computer had to be calibrated to the specific geometry of the aircraft in which it was installed. The distances between sighting stations and turrets varied slightly from airframe to airframe, and each parallax correction had to be individually programmed. One technician who performed these alignments recalled arriving at Marietta to find completed B-29's lined up for a mile waiting for their gun systems to be adjusted. Civilians hired by the government for the alignment work were sometimes found sleeping inside the pressurized crew tunnels during their shifts. The work was tedious, critical, and seemingly endless. The system was not perfect. No defensive gunnery system could be. The B-29 had blind spots, areas from which a fighter could approach without entering the effective field of fire of any turret. The most significant was the forward upper sector. The upper forward turret could traverse forward, but its arc was limited by the fuselage, the cockpit, and the wings. When firing forward, only 2 of the 4 guns in the turret could be brought to bear. The other 2 were ballistically blocked by the aircraft's own structure. This created a zone directly ahead and slightly above where the B-29 could fire only 2 guns instead of the 4 or more that other sectors provided. Japanese fighter pilots discovered this vulnerability through combat experience and exploited it systematically. The head-on attack became the preferred Japanese tactic against B-29 formations. A fighter would climb above the bomber stream, roll into a diving attack from directly ahead, fire a burst aimed at the cockpit, and pass underneath or to the side before the lateral turrets could engage. The closing speed was so fast, often exceeding 600 miles per hour, that the computer had difficulty tracking the target, and the gunner had only seconds to acquire, range, and fire. The Japanese threw everything they had at the B-29. The Nakajima K-44 Shoki, Tojo in Allied code, was a fast, heavily armed interceptor that could reach the B-29's operating altitude. The Kawasaki K-45 Toryu, Nick, was a twin-engine heavy fighter armed with cannon that could do serious damage in a single pass. The Mitsubishi K-46 Dyna, originally a reconnaissance aircraft, was converted to a high-altitude interceptor and pressed into the anti-B-29 role. Even the aging Nakajima K-43 Hayabusa, Oscar, was used, despite being underpowered and lightly armed for the task. The most desperate Japanese tactic was ramming. As the war progressed and conventional interception became less effective, partly because of the B-29's altitude, partly because of the central fire control system's increasing reliability, Japanese pilots began deliberately flying their aircraft into B-29's. These were not kamikaze attacks in the traditional sense. The pilots sometimes survived by bailing out after impact, but they reflected a willingness to sacrifice aircraft and possibly lives to destroy the bombers that were systematically burning Japanese cities. Photographs taken by gun cameras mounted on B-29 turrets. Each turret had provision for a GASAP camera that continued recording for 3 seconds after firing ceased, captured images of Japanese fighters flashing past at impossibly close range, some passing so near that the camera recorded individual rivets on the fighter's fuselage. These photographs documented both the skill of the Japanese pilots and the effectiveness of the fire control system. Many of the fighters captured on film were trailing smoke or shedding debris, hit by computer-aimed fire at ranges that manual gunners could never have achieved. The B-29 also had vulnerability zones below the fuselage. The lower turrets had restricted upward arcs, and the belly of the aircraft, between the lower forward and lower rear turrets, had a sector where neither turret could depress its guns far enough to engage a fighter approaching from directly below. Japanese pilots learned to fly under the bomber formations and pull up into attacking climbs through this zone. The Army Air Forces responded with modifications. The upper forward turret was upgraded from 2 to 4 50-caliber guns on many aircraft, providing increased firepower in the forward sector. Tactics were developed to minimize the head-on vulnerability, formation flying that provided mutual defensive coverage, and evasive maneuvers designed to present the attacker with a crossing angle rather than a straight-on approach. But the fundamental solution was not tactical, it was technological. The central fire control system, for all its blind spots, gave the B-29 a defensive capability that no other bomber possessed, the ability to concentrate the fire of multiple turrets on a single target from any angle with computer-calculated accuracy. A Japanese fighter that avoided the forward blind spot and attacked from the beam or the quarter would find itself in the overlapping field of fire of 2, 3, or 4 turrets, 8 to 16 50-caliber machine guns, all aimed by computers that corrected for every variable that a human gunner could not calculate. The Central Fire Control System arrived in combat in June 1944 when the first B-29 missions were flown from bases in India and China against Japanese targets. The system did not work. The problems were numerous, severe, and, in some cases, dangerous. The most alarming was a wiring defect that caused turrets to slew uncontrollably. A gunner would press the trigger, and instead of firing in the direction the sight was pointing, the turret would rotate 20 degrees and spray its entire ammunition load, 1,000 rounds, in a random direction. The rounds might hit another B-29 in the formation. They might hit the aircraft's own tail. The defect was caused by bad wiring design and occasionally defective wiring harnesses, manufacturing errors in the miles of electrical cable that connected the sighting stations to the computers to the turrets. This fault was not identified and corrected until January 1945, 7 months after the B-29 had entered combat. For those 7 months, American gunners fought with a system that might, at any moment, begin firing uncontrollably in a random direction. General Curtis LeMay, who commanded the B-29 force, was characteristically blunt in his assessment. He cataloged scores of defects in the B-29, some apparent on the ground, others appearing only at altitude during combat operations. The fire control system was among his primary complaints. The 200-pound computers were delicate instruments operating in an environment of vibration, temperature extremes, and the constant jarring of turbulence and combat maneuvers. Their build quality was inconsistent. The vacuum tube electronics were fragile. The mechanical components required precise calibration that was difficult to maintain under field conditions. The crews, many of whom were poorly trained on the new system, there had not been enough time or enough operational aircraft for thorough training before deployment, struggled with troubleshooting procedures that required technical expertise they did not possess. The operating manual was dense, technical, and written for engineers, not for 20-year-old enlisted gunners who had been trained on manually aimed machine guns. One B-29 blister gunner, Frank "Bud" Farrell, later described an incident during LeMay's low-level night raids. When LeMay ordered all guns except the tail removed for the nighttime firebombing missions, Farrell's crew quietly disobeyed the order. They loaded 100 rounds into the lower aft turret, just in case. On 2 separate night missions, the left gunner spotted a Japanese night fighter by its muzzle flash and shot it down using the fire control system's targeting capability. The crew could not claim the kills for fear of court-martial. They had been ordered to remove the guns. 11 lives were spared by an act of insubordination and a fire control system that worked precisely as designed, in the dark, against a target visible only by its own gunfire. Despite these problems, the system worked often enough to demonstrate its potential. When the computers functioned correctly and the gunners tracked their targets smoothly, the results were devastating. Japanese fighters that had approached B-17 formations with relative impunity found themselves engaged at 900 yards, a range at which their own weapons were ineffective, by computer-aimed fire of startling accuracy. The effective range advantage alone, 900 yards versus the 400 to 600 yards of manually aimed guns, meant that the B-29 could kill a fighter before the fighter was close enough to fire back. In March 1945, Curtis LeMay made the most controversial tactical decision of the air war against Japan. He ordered the B-29 force to abandon high-altitude daylight precision bombing and switch to low-altitude nighttime incendiary raids on Japanese cities. The decision was driven by the failure of high-altitude bombing to achieve results. The jet stream at 30,000 feet over Japan scattered bombs across miles of landscape, making precision targeting impossible, and by the realization that Japanese night fighter capability was virtually non-existent. If the bombers flew at night at altitudes between 5,000 and 9,000 feet, they could carry more bombs, hit more accurately, and face minimal fighter opposition. LeMay ordered the guns removed. All 4 remote-controlled turrets, upper forward, upper rear, lower rear, were taken off the aircraft. The 5 analog computers were removed, the Amplidyne generators, the Celsin transmitters, the miles of wiring, all removed. Only the tail turret was retained with its 2 50-caliber machine guns as a minimal defensive measure. The weight savings were enormous. Each turret weighed several hundred pounds. The 5 computers weighed 1,000 pounds. The ammunition, over 6,000 rounds of 50 caliber, weighed another 1,000. The total weight reduction was approximately 6,000 pounds per aircraft, weight that was replaced with additional incendiary bombs and fuel. The stripped-down B-29's flew over Japan at night, low and fast, carrying nothing but bombs and the tail gunner's 2 guns. The firebombing campaign that followed, beginning with the Tokyo raid of March 9th to 10th, 1945, which killed an estimated 100,000 people and destroyed 16 square miles of the city, was the most destructive air campaign in history, more lethal in its immediate human cost than either atomic bomb. The central fire control system had been designed to protect the B-29 from fighters. LeMay made the system irrelevant by eliminating the fighter threat through tactical innovation. The guns came off because the enemy could not find the bombers in the dark. The guns came back. When the B-29 returned to daylight operations, for specific missions, for atomic bomb delivery, and for the continued strategic campaign against Japanese industrial targets, the central fire control system was reinstalled. The wiring defects had been corrected in January 1945. Improved training programs had produced gunners who understood the system better. Field modifications, developed by crews and maintenance personnel, had improved reliability. The Enola Gay, the B-29 that dropped the atomic bomb on Hiroshima on August 6, 1945, was modified specifically for atomic delivery. All guns were removed except the tail turret. The aircraft was stripped to minimum weight to compensate for the mass of the bomb. The tail gunner, Staff Sergeant George Robert Caron, was the only defensive crew member. He sat in his station, watching the sky behind the most important aircraft in the history of warfare with two .50 caliber machine guns and a fire control computer that was no longer connected to any other turret on the aircraft. After the war, the B-29 continued in service. It flew combat missions in the Korean War, where the central fire control system was tested against a new and vastly more dangerous threat, the MiG-15 jet fighter. The MiG-15 was faster than any fighter the B-29 had faced in the Pacific. It could climb to the B-29's altitude in minutes, attack from any direction at closing speeds that exceeded 700 miles per hour, and escape before the turrets could track it. The analog computers, designed to calculate corrections for propeller-driven fighters approaching at 350 miles per hour, struggled with targets moving at jet speeds. The mechanical response time of the system, the lag between the gunner's sight movement and the turret's physical response, was too slow for jet combat. Despite these limitations, B-29 gunners in Korea are credited with shooting down 27 aircraft, including at least one MiG-15. Soviet records confirm that one MiG-15 was shot down by B-29 defensive fire on December 6, 1950. The pilot, Lieutenant N. Sarakov, was killed. It was a remarkable achievement for a system designed in 1942 to fight propeller-driven fighters, and it was also the system's last hurrah. After the loss of 28 B-29s in Korea, future Superfortress raids were restricted to night missions, and the era of computer-controlled defensive gunnery on manned bombers effectively ended. The B-29's central fire control system was, simultaneously, one of the most brilliant engineering achievements and one of the most troubled weapons systems of the Second World War. It was brilliant because it solved a problem that was mathematically insoluble by human means. No gunner, no matter how skilled, could calculate lead, drop, windage, and parallax corrections simultaneously, continuously, and in real time while tracking a fighter closing at 600 miles per hour. The computer could. And when it worked, when the wiring was correct, the calibration was accurate, the vacuum tubes were functioning, and the gunner tracked smoothly, it delivered defensive fire of unprecedented accuracy at ranges that made the bomber untouchable by fighters armed with weapons effective only at 400 yards. It was troubled because it was too complex for its era. The analog computers were delicate, the electrical system was fragile, the manufacturing quality was inconsistent, the training pipeline was inadequate, and the tactical environment changed faster than the system could adapt, from high-altitude daylight precision bombing to low-altitude nighttime incendiary raids and back again, each transition requiring the system to be installed, removed, and reinstalled. The Singer Company's contribution deserves particular recognition. A sewing machine manufacturer in New Jersey produced over 20,000 fire control computers, precision analog devices of extraordinary complexity, at a rate that eventually exceeded 500 per week. This was the same pattern seen across American wartime production. Companies with precision manufacturing expertise, refrigerator makers building binoculars, car radio companies building walkie-talkies, sewing machine companies building fire control computers, applying civilian industrial skills to military problems that the traditional defense industry could not solve alone. The B-29's $3 billion price tag, $1 billion more than the Manhattan Project, bought the most expensive aircraft program in history. A significant portion of that cost was the fire control system. The 5 analog computers, the 5 remote turrets, the Amplidyne generators, the Celsin networks, the miles of wiring, the optical sighting stations, the precision manufacturing, the alignment and calibration. All of this represented an investment in defensive technology that was, in the final months of the war, removed from the aircraft and left on the ground so that the bombers could carry more firebombs. The irony is complete. The most sophisticated defensive gunnery system ever built was most effective when it was not used, because LeMay found a way to make the bombers invulnerable without it, by flying at night when the enemy could not see them. But the technology survived. The principles of centralized fire control, computerized ballistic correction, remote turret operation, integrated weapons management became the foundation of every subsequent aircraft weapon system. The B-36 Peacemaker, which succeeded the B-29 as America's strategic bomber, carried an improved version of the central fire control system with faster computing and jet-age tracking capability. The concepts pioneered in the B-29's 5 General Electric computers, automated lead calculation, real-time parallax correction, sensor-to-weapon data integration, are the direct ancestors of the fire control systems in every modern fighter aircraft, from the F-16 to the F-35. The Japanese fighter pilot who dove headlong at a B-29 in 1944, aiming for the blind spot that his intelligence briefing had identified, was fighting the last war. He was attacking a bomber defended not by men with guns, but by a machine that could think faster than he could fly. The machine had blind spots. The machine had failures. The machine was sometimes more dangerous to its own crew than to the enemy. But the machine was the future. And the future, built by General Electric engineers and Singer sewing machine workers, assembled in a Georgia factory and calibrated by technicians who found civilians sleeping in the pressurized tunnels, won.